Maclaurin series. So, first thing we need to know about Maclaurin series is they were discovered, I suppose, by a Scottish mathematician, Maclaurin, and these are the special case of the Taylor series, and that is when the Taylor series is centred around 0. So just before and just after 0, these should be a pretty good approximation to sin, cos, tan, exponentials, logs, all that kind of stuff. Maybe put a equals 0. Right, so a formula for our approximation is that f of x is equal to f of 0, you can remember a is 0, plus f dashed of 0, x take away 0, which is x over 1 factorial, plus f double dashed of 0, x take away 0 squared, so that's just x squared, over 2 factorial, plus f triple dashed of 0, x cubed, over 3 factorial, and so on, all the way up. Remember, that's because x equals x take away 0 is just x. So all it is the Taylor series formula, but put in 0 where we put in a from before. Right, example number 1. Find first 5 non-zero terms in the Maclaurin expansion of f of x equals 1 over 1 plus x. I suppose it could be 1 over x plus 1, whatever way you want to think about it. Right, so as usual with a Taylor and Maclaurin series, you need to calculate your derivatives and you need to calculate your coefficients. Right, so f of x we start off with is 1 over 1 plus x, so that means that f of 0 is 1 over 1 plus 0, which is just 1. Okay, now I can't differentiate something that looks like that yet. I've got to make it 1 plus x to the power of negative 1. Now we can differentiate it using the chain rule. So f single dashed x is negative 1, 1 plus x to the power of negative 2 times 1, which is just leaves it the way it is, which is just negative 1 over 1 plus x squared. That means that f dashed of 0 is negative 1 over 1 plus 0 squared, which is negative 1. Okay, f double dashed of x, well, we're just going to use this one here, because that's in the right form to differentiate, so that becomes 2, 1 plus x to the power of negative 3, which is 2 over 1 plus x cubed, which is 2. So I've got 3 coefficients so far. I wanted 5 terms, so I need 5 coefficients. So I need to differentiate again. And again, I'll just use this one here. So that's negative 6, 1 plus x to the power of negative 4, which is negative 6 over 1 plus x to the power of 4. So f triple dashed 0 is negative 6 over 1 plus 0 to the power of 4 which is negative 6. I've got 4 coefficients now, 1, negative 1, 2 and negative 6. I know I need to do one more. So the fourth derivative of x is, again, use this one here, 24, 1 plus x to the power of negative 5. Which is 24 over 1 plus x to the power of 5. Which is 24. So there we go, I've got my 5 coefficients. I've got 1, negative 1, 2, negative 6 and 24. Right, so your formula f of x is equal to f of 0 plus f dashed of 0 x over 1 factorial plus f double dashed of 0 x squared over 2 factorial plus f triple dashed 0 x cubed over 3 factorial. 1, 2, 3, 4, 5 terms, 4, 0, x to the power of 4 over 4 factorial. That's my formula. Now I'm going to substitute in my numbers. Right. So f of 0 was 1. F dashed of 0 was negative 1. F double dashed of 0 is 2. Right, that's a 2x squared. Take away our plus negative 6 x cubed over 3 factorial plus 24 x to the power of 4 over 4 factorial. Sorry about that wee mess there that I've made there. Right, simplify. So that's going to give me 1 take away x over 1 plus 2x squared over 2 take away 6x cubed over 6 plus 24x to the power of 4 over 24. So isn't that lovely? That means that the Maclaurin expansion is 1 take away x plus x squared take away x cubed plus x to the power of 4. So you could probably guess what would happen to the rest of the series. Take away x to the power of 5 plus x to the power of 6. You can see it's just the same thing over and over again with changing signs. Okay, so the Maclaurin expansion, or another way of estimating 1 over 1 plus x is around 0 is to use this polynomial here. Okay, right, let's look at an example 2. And these ones are far more prevalent. These are the ones that will come up a lot. And I'm just going to write it in a slightly different way. Find the Maclaurin series expansion down to the x to the power of 7 term for f of x equals cos x. Right, so derivatives and coefficients. Right, so f of x is cos x, so you always write the function first, you don't differentiate it, right? And then we put in 0, which is cos of 0, which is just 1. dash of x, which is negative sine x, which is negative sine 0, which is 0. Double dash of x is negative cos x, so f double dash of 0 is negative cos 0, which is negative 1. F triple dash of x is sine x, so f triple dash of 0 is sine 0, which is 0. Now, we want to go all the way to the x to the power of 7 term, so that means we need to go all the way down to the 7th derivative. Okay, so let's just keep going. Now, sine and cos is dead easy because it's just a pattern. The fourth derivative of x is going to be cos x. The fourth is cos 0, which is 1. The fifth derivative of x is going to be negative sine x. The fifth derivative of 0 is negative sine 0, which is 0. Sixth derivative of x is negative cos x, which is the sixth derivative of 0. Negative cos 0, which is negative 1. The seventh derivative of x is sine x, which is sine 0, which is 0. So there we go. So we're just alternating cos becomes negative sine, which becomes negative cos, which becomes sine, which becomes cos, which becomes negative sine, which becomes negative cos, which becomes sine. Right, so I'm going all the way up to x to the power 7 term, so f of x is going to be f of 0, right, f of x is going to be f of 0 plus f dashed of 0 x for 1 factorial plus f double dashed of 0 x squared over 2 factorial plus f triple dashed of 0 x cubed over 3 factorial plus the fourth derivative of 0 over the power of 4 over 4 factorial plus the fifth derivative of 0 x to the power of 5 over the fifth derivative, sixth derivative of x equals 0, x to the power of 6 over 6 factorial plus the seventh derivative of x at 0, x to the power of 7 over 7 factorial. Right, annoying, yes. But it's quite straightforward. So all we're going to do is we're going to swap in our coefficients. So f of 0 is 1, f dashed of 0, 0, f double dashed of 0, negative 1, f triple dashed of 0, 0. Right, so that is f of x is 1 plus 0x over 1 factorial plus negative 1 x squared over 2 factorial plus 0x cubed over 3 factorial plus 1 x to the power of 4 over 4 factorial plus 0 x to the power of 5 over 5 factorial plus negative 1 x to the power of 6 over 6 factorial plus 0 x to the power of 7 over 7 factorial. So just substitute those all in. Okay, so f of x is 1 take away x squared over 2 plus x to the power of 4 over 24 take away x to the power of 6 over 720. That's us done. There's only 4 terms because I've got that one, that one, that one, and that one cancelling out because they've all got a coefficient of 0. So that is my Maclaurin expansion down to the x to the power of 7 term for f of x equals cos x. Okay, so in the Maclaurin series booklet, the Taylor Maclaurin series booklet on page 18, you could try questions 2, A, B, and E. And we'll need to put the booklet up in Teams. Remind me to do that. If I haven't done that, please moan at me and get me to do it. Right, now you need to be able to prove how you can get the Maclaurin expansion for sin, cos, exponentials, logarithms, 1 over 1 plus x, which is the one I've done today. Right, you need to be able to prove that you can do all of those. Now, the good thing about these expansions is that they are good bases that allow us to find more difficult Maclaurin expansions. Okay, so standard okay, now you must be able to prove how you get each expansion below from derivative to coefficient, like the examples above. So you must be able to show how you get these, right? But what they do is these four provide good bases for more difficult expansions, right? So the first one is sine x, and sine x's expansion is x, take away x cubed over 3 factorial plus x to the power of 5 over 5 factorial, take away x to the power of 7 over 7 factorial plus. So you can see that the sine one, all the powers are odd numbers. Power of 1, power of 3, power of 5, power of 7. Right? So the sine's the odd one. And you must be able to prove that just like the ones we did above, like 2. Cos x, the one we just did, which is 1, take away x squared over 2 factorial, plus x to the power of 4 over 4 factorial, take away x to the power of 6 over 6 factorial, plus a whole lot of other nonsense. Okay, now you see that the signs alternate. Right, another one you need to be able to use and prove is that the exponential is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x squared 4 over 4 factorial plus and on and on and on. The exponential is always at plus and it has every single term in it. As you can see, sin and cos, the signs alternate. And the last one that's useful for us to know is that ln 1 plus x is x, take away x squared over 2, x squared over 2 plus x cubed over 3, subtract x to the power of 4 over 4 plus x to the power of 5 over 5, take away x to the power of 6 over 6, plus a whole lot of other stuff. So hopefully you can see for that is that it's got every term in it apart from 1, and there's no factorials on the bottom, because the factorials are cancelled out by the terms we get on the top when we find the coefficients of the derivatives. So you must be able to prove, like we did in example 1 and 2, how you get each of those. Okay, but what it allows us to do, as I said, is find more complicated series. Right, so this is using standard example 1. So remember, all the Maclaurin expansion is doing is providing a good approximation at around the point 0. So rather than using sin, I can just use a normal polynomial. Rather than using an exponential, I can use a polynomial. So use the standard expansion of sin x up to the x to the power of 6 term to find the expansion for f of x equals sin x. Okay, now those standard Maclaurin expansions are in the book. There's a table of them. But I think there's 5 in the table, but I'm all interested in those 4. So, what I do is I see that I have a standard Maclaurin expansion for sin x. So I'm going to write that down first. So sin x would be as x is equal to x cubed 3 factorial plus x to the power of 5 for 5 factorial take away x to the power of 7 over 7 factorial, etc. Right? Now, all I'm interested in is up to the x to the power of 6 term. Right? So I know I'm not going to use that. Right? So I know I'm only going to be involved in these 3 terms here. Right now, what's different about my function is where my x normally is, I've replaced that with 3x. So in my function, I need to replace x with 3x. So wherever I put an x, I need to put in 3x. But I need to put that 3x in a bracket. Like that. And now I've got the Maclaurin expansion up to the x to the power of 6 term for sin 3x. I'm just going to simplify it though. That's 3x. That would be, remember you've got to cube the 3 and the x, that would be 27 x cubed over 6. And then I've got to 3 to the power of 5 and x to the power of 5, so that's 243 x to the power of 5 over 120. And then I can simplify the fractions. Sin 3x is 3x, take away 9x cubed over 2 plus 81x to the power of 5 over 40. Okay. Example 2. Right, okay, so this time I see that I've got cos x, so I'm going to write down my expansion for cos x. So cos x is 1 take away x squared over 2 factorial plus x to the power of 4 over 4 factorial, and I only need up to x to the power of 6 term, take away x to the power of 6 over 6 factorial. So that's me written down the standard expansion. Now in the exam, or assignment, you're going to have to be able to prove that standard expansion. Let me say cos x squared over 4. So what we're doing is we replace every single x with x squared over 4. Four factorial is 24. $720. Like that. Right, now so what we've got to watch here is that we square the top and square the bottom. So that's going to be x to the power of 4 over 16 over 2 plus x to the power of 8 over 4 to the power of 4 is 256 over 24, subtract x to the power of 12 over 4 to the power of 6 is 4096 over 720. Right, so 16, oh no, that is. And remember that 16 joins the 2 in the bottom, so that's going to be 32. Six, 1, 4, 4. That's x to the power of 12 over 2949120. So that is the Maclaurin expansion for cos x squared over 4 down to the x to the power of 6 term. No, it's down to the x to the power of 6 term for cos x, and then you just let whatever term you get at the end. Okay. Right. Now I want to just finish this off by just doing an exam type question. I'll just run through everything I could ask you about Maclaurin expansion, or Maclaurin series expansion, and the exam. Right, so A, show the Maclaurin of e to the power of x down to the x to the power of 4 term as e to the power of x equals 1 plus x squared over 2 plus x cubed over 6 plus x to the power of 4 over 24. B. Hence, find the Maclaurin There we go. So show the Maclaurin expansion of e to the power of x down to the x to the power of 4 term as 1 plus x squared over 2 plus x cubed over 6 plus x to the power of 4 over 24. Then, hence find the Maclaurin expansion down to the x to the power of 8 term for f of x equals x squared. Then it's asking you to integrate between 0.1 and 0.5, 1 over x squared dx. Right, so this is how a typical assignment question would be asked on this. 3 parts, right, so part 1. Right, so f of x is e to the power of x. So that means that f of 0 is e to the power of 0, which is 1. So I'm just doing my derivatives and my coefficients. So f dashed of 0 is e to the power of x. For the exponentials, it's really easy because the exponential just stays the same the whole way down. And I want up to x to the power of 4 terms, I need to do 4 derivatives. And I know it's self-explanatory, but you need to show all 4 derivatives if you were to get a mark in this question. So that's me done. Right, so f of x is f of 0 plus f dashed of 0 x over 1 factorial plus f dashed of 0 x squared over 2 factorial plus f triple dashed 0 x cubed over 3 factorial plus f the fourth derivative 0 x to the power of 4 over 4 factorial. Right, so 1 plus 1x over 1 plus 1x squared over 2 plus 1x cubed over 6 plus 1x to the power of 4 over 24. So that means that f of x, or e to the power of x, is 1 plus x squared over 2 plus x cubed over 6 plus x to the power of 4 over 24. So if you wanted to model e to the power of x without having an exponential button in your calculator, without knowing what an exponential was, you could model that exact function about 0 using that polynomial there. Right, next. Part B. Hence, find the Maclaurin expansion of f of x squared. Right, okay, so e to the power of x, we're saying is 1 plus x squared over 2 plus x cubed over 6 plus x to the power of 4 over 24. Right? So all I'm doing is, wherever I've got x, I'm going to swap it for x squared. So that means that and that's me done. Now obviously it's not going to be as easy as that. There's going to be fractions and stuff involved, but I just want to show you the steps that would be involved in an assignment type question, right? See, hence, now hence always means what does hence always mean? Hence always means you've got to use part A, B, or part A or B to do this, right? So the nice thing about this is now that's a pretty impossible function to actually integrate. a way of looking at it is you can maybe try to do integration by substitution, but I don't think it's going to work. So what I'm going to do is I'm going to swap my e to the power of x squared for my polynomial version. Like that, dx. Right, now, we know 1 over x, which means divide everything by x. Like that. So I just multiplying everything by 1 over x, basically, all the way along. Right. So 1 over x times 1 is 1 over x, 1 over x times x squared is x, etc, etc, etc. Right, now, remember we've got to integrate this now. Now, we change the limits, because it's definite integration. Now, remembering how you differentiate 1 over x. 1 over x, if you differentiate it, you don't make it x to the power of negative 1, because that doesn't work. You differentiate 1 over x, it's ln x. So that's plus x squared over 2, plus x to the power of 4 over 8, plus x to the power of 6 over 36, plus x to the power of 8 over 8 times 24. 192. There we go. So remember, integrate, you add 1 to the power, divide by the new power, add 1 to the power, divide by the new power, add 1 to the power, divide by the new power. Right, okay, so we're now swapping 0.5 and 0.1, so ln 0.5 plus 0.5 squared for 2 plus 0.5 to the power of 4, 8 plus 0.5 to the power of 6 over 36 plus 0.5 to the power of 8 over 192. Take away ln 0.1 plus 0.1 squared over 2 plus 0.1 to the power of 4 over 8 plus 0.1 to the power of 6 over 36 plus 0.1 to the power of 8 over 192. And we're just doing the same thing, but you've substituted in 0.1 instead of 0.5. Oh, okay, I'm not carrying it over. Right. Right, so that's type that into the calculator. So ln 0.5 plus 0.5 squared over 2 plus 0.5 to the power of 4, 0.5 to the power of 4 over 8 plus 0.5 to the power of 0.5 to the power of 6 over 36 plus 0.5, keep doing that, 0.5 to the power of 8 over 192. That gives me negative 0.56. Right. Then I'm just going to do the same thing, but type in 0.1. and that gives me negative 2.30. So 2.30 take away 0.56 is 1.74 units squared. And that is me integrated between 0.5 and 0.1, 1 over x e to the power of x squared, which is something which would have been impossible until now. So please have a look at those questions I gave you to have a look at. I will do linear approximations during the next lecture, and I'll put those booklets up online. I hope everyone's doing well.